So, welcome colleagues who are joining us here in the Institute of Advanced Studies in person, and those of you whom I can see are just beginning to join us online. So very much welcome. My name is Marcia Meskimen. I'm the director of the Institute of Advanced Studies. We're very, very pleased to be able to be welcoming a residential fellow today, Dr. Wenbo Ding, who is coming to us from Tsinghua University, and we'll be doing a very interesting seminar. For those who have never joined us before online, let me do a little housekeeping though. If you are online, you will find that there is a chat function on your Zoom webinar button, and there is also a Q&A function on that. We will monitor those throughout the talk, so please do feel free to use them, and we will make sure that we feed in that conversation to the wider conversation after the seminar. So they are live, they are working, and we are listening for that. We are also monitoring, we'll monitor the sound a bit during the course of the seminar, but if you're having any technical problems, please do also notify us and we can usually address those. And for those of you who are joining online, we are recording the seminar, but we are not recording any of the Q&A. We will not be keeping anybody's data in any way. We're not managing your data in an illicit way. We will cut all of that away. But the seminar itself, if you want to hear it again, or if you know colleagues that wish to join and were unable to be here today and want to see it again, will probably appear in about a week's time live on the IAS website under the video library. So for information, that's how it's operating. So again, welcome to the Institute. We are thrilled to be welcoming Wenbo, and really delighted that you are here, really delighted you have made it. We have waited for you for some time.
For 2 years.
Yes, and are very, very thrilled. And this is a very interesting area for us at the institution. And I want to be able to, hopefully you'll note already that the room is full of colleagues who come from different parts of this institution and have an interest in this area that you're working in. So I think this is very exciting for us because it helps us to foster not only the international, but the interdisciplinary discussions that we like to foster through the Institute. So very, very delighted. And I'm going to turn over to my colleague, Ishara Dharmasena, who is a Royal Academy Engineering Research Fellow and also a lecturer here at the university, who is going to do a much more detailed introduction and talk a bit about how you're integrating into the university and some of the collaborative work that you're doing. So with that, very much welcome, Ishara.
Thank you. Professor Wenbo Ding is associate professor at the TBS site, Tsinghua Birth Extension Institute at Tsinghua University. He's an expert in a wide range of areas, including self-powered centers, energy harvesting, wearable devices, soft robotics, signal processing, and mobile computing and all. And he's currently the lead of the Smart Sensing and Robotics SAR lab at the TBS site. I know Wenbo since 2018 when we first met at Professor Zhongling Nang's laboratory, where he was working as a postdoctoral research fellow, and then he moved to the Tsinghua University and then got his position at the TBS site. And since then, we have been working closely on different areas like self-powered sensing, energy harvesting, and wearable electronics. Currently, our project related to the IAS program is on developing smart body area networks using self-powered sensors and energy harvesting methods for health sensing applications. And those who are interested in his expertise areas, please get in touch with Dr. Wenbo and then make collaborations and associate him with the different research areas that you want to discuss. Thank you.
Thank you.
Okay, so now it's my turn, and I will first of all, I would like to thank Ishara for actually almost we have met for 5 years and 6 years when we're both students or even the early career researchers, and we actually make very good, tight collaboration. And after this IS fellowship, we also successfully granted by another Royal Society collaboration between the UK and China. It's really very competitive. I would like to say also, without the IS fellowship, they cannot see our pre-joint like the collaboration. I would like to thank Marshall and all of us. And also, I would like to appreciate my insistence, right? Because of COVID, I know all of us, you know that when I was awarded the fellowship, really humble to get that when 2 years ago. But I found it difficult to get out China because of the border like the limitations. And then I insisted I must come look for this lovely town and lovely university in person. So I just defer this almost twice. Yeah, and then when we come to this lovely place, but unfortunately I plan to stay here for at least 2 weeks. But due to some like issues, I can only stay 1 week. But I will come maybe in the next 2 years, maybe 2 or more times, to keep interacting with you guys. And first of all, secondly, I would like to thank Marshall and all of our staff and faculty in IS, which actually not only give me the support during all the arrangement, but also give me actually these opportunities to be awarded. Because when I look at all these names, especially the name list of them, there are too many very big names. Like I mentioned that, like the Jianwei Zhang from University of Hamburg. It is last year's fellow. He's actually the big name in the robotics. And also the Jason Ren, maybe you know that, is a professor in Princeton. But actually we are not in the same field, but I know him very well. He's a very, very top scientist from China. So I really humbled to be awarded, even though I'm actually 2 years ago, I was assistant professor. And when I was awarded the fellowship, I got promoted, right? It's actually part of these kind of things. So thank you all for this support and for this award, and also Karen. So today my topic will roughly, actually part of my research, but actually I think it's really interesting to show you, is our recent progress on robotics and more on the flexible tactile sensing. So so first of all, let me introduce a little bit on myself. So as Marshall mentioned, that IS is an interdisciplinary institute, and also my experience also is actually cross different fields. I do the wireless communication, more than signal processing, when I doing my PhD training, and then I joined various to a new field when I do my postdoc training. I also got another offer from MIT doing the wireless communication and information theory, but I think it's too boring, right? Because everyone deal with the calculations and the equations. It's not my strength, even though I can do well in that field. So I tried to go into the field of the sensors. And then I got offer from VL1, a very top expert in the field of soft sensors and nanogenerators. So with this 3 years training, I go into a new field. I think I can combine the algorithms and the hardware and the software together. So when I going back to China, joined a new, actually this is the Tsinghua Berkeley Sensing Institute, is a new institute, but established within Tsinghua and the Shenzhen government and also the UC Berkeley. But what they actually want to establish kind of institute is not doing this traditional research. They want doing the actually really interdisciplinary research. So actually, so I feel really lucky to join this kind of institute, because in this field, in this institute, I can like recruit the students from different backgrounds, like the mechanical engineering, material science, and also even the like for some human science, human research. In my lab, and we can do really like interesting things. So actually, so today's outline for the talk will be so maybe I think I should keep near to the microphone. Yeah, well, will be the 4 parts, and the first part I will talk about. We are doing some sensing part for the robotics based on some techniques, and second part will with this kind of sensing techniques. And we are actually boost or enhance some like grasping and recognition for the robotics. And first of all, let me introduce some like background. So this is actually the last year, like the Facebook changing his name to Meta, but actually tell a old story, because we all know the virtual reality and augmented reality for many years. When I was a middle school student, I always play some games, right? 3D games and some other like virtual reality games. But actually, in that part, we only consider it as games, as entertainment. But when the Meta or some other big companies, like the unicorn companies, tell the new stories, the virtual reality is not only related or limited to the games or entertainment. They can also be applied in many fields, like the medical treatment and the surgery, and even for some like emotional treatment, right? If we are, if this like this kind of thing. So there is actually another like opportunities, a lot of opportunity and potential in this field. So this is really exciting. But when we look at this is actually the medical glove released last year by the McGovern. And when we see the gloves, first of all, the glove is really, really bulky, even though it's actually this is advanced. So that's actually the first thing. The second thing, this glove costs a lot. For instance, this glove I asked a friend from Meta who is in the group. So even though they have very mature supply chain to support this kind of demo prototype, but it still cost about $100K for this single device. And also this is only the prototype for your glove, but also there is a lot of bulky facility to support, like the air and some other pressure facility to do this. But this is good because Meta has tell us how the virtual reality or the gloves will be. And this is some sensors behind of the gloves. And not maybe it's not exactly the same thing, but actually this is the past decades. A lot of very successful commercial companies doing something, and also some top universities. So this is the biotech. Actually, it's similar to your finger, and it can do some like the thermal resistor and some other like the tactile sensing. And this is one. My lab has purchased one. It's about $3,000, but it can be used 3,000 times. So that means every touch it will cost $1. Yeah, because of the durability of the materials and some other like electronics. And here is a delta proposed by MIT, the very, very famous and the mainstreaming of tactile sensing recently, which I believe will be the mainstreaming in the future. But I still have some other limitations that actually our group is actually aiming at in this field and to do some very inspiring things. And well, let's start from the story. So why we are curious about the tactile or the friction. This is one paper published. This is actually published in Nature as a perspective paper in 2021. And it's actually, I think maybe you or one of you are aware of this professor, or he's actually a very good writer in physics. It's from UK, and he has actually this paper, our Nature paper is just to want to promote this kind of book. The book is Sticky, the secret science of surfaces. And the Nature has tell a very good story. The story can be briefly looking like that. Without friction, without tribal, what the world will become? Actually, they tell very, very huge and horrible story. Without the friction, you will have no fingerprints. You will have no, and will have a very, very large impact to the climate. So maybe the climate will be cooling down because a lot of heat and will be generated by friction, like our mechanical, like something like that. And without the friction, maybe the Earth, the temperature of the Earth will be lower about 10 degrees. But actually, we cannot get rid of the friction, and also it has a lot of information. If you shake it with Marshall and shake it with Ishara, the friction, like the coefficients, will give you different, like the internal, like the feeling, right? This is actually the story why we want to know the nature of friction. And so how about the power of friction? So there's actually another meaning. So let's look at the very old picture from from China, the terracotta warriors, the foot, the back of the foot, the show. It's actually we can see that almost 3,000 years ago, our ancients can know how to improve the friction when they're doing the marching, right? So this is actually the old tribology. But our modern tribology, as we mentioned, that if you are from the field of mechanical engineering, you must know you want to reduce the kind of friction, right? Because reduce the friction means improve the efficiency in some other, or improve the durability. Especially tear and wear of the materials will cause a lot of like the bad things to your thing. But Professor Liu Wang has mentioned that actually there is some energy inside the friction. So this is actually another phenomenon which has been observed almost 2,000 years. This is triboelectrification. So that means two different materials. Generally speaking, there are two different materials, especially when you wear a wool, like wool shirt, or you are touching with some like the rubber or something like that. They generate charges, right? So this is actually the very, very well observed phenomenon. And how to determine the charging fraction? It's actually, there is a triboelectric theory, but actually now Sarah has done some very, very good modeling work on this kind of things. Really review the truths or real, like the working mechanism between the materials, triboelectrification. For example, as we all know, or maybe if you're learning something in your middle school textbook, only two different materials, they can generate charges. But actually, when we go into this field, even the two identical materials, they can generate different charges. So actually there are two, and also when we also consider the solid, like the material, but actually when they turn into liquid or turn into air, they can also generate the charges. So that's actually this is the motivation of how we want to investigate that kind of thing. And also when we think that if when two materials get charges, they will become a capacitor, equivalent capacitor. So that means it can be working as a energy harvester and also the sensor. So that's actually support this kind of motivation of our field. So so this is actually let's come back to 2012 when the first paper published from Professor Zhe Wang's group. It's actually a new phenomenon and also a new field that is called triboelectric and nanogenerators. So I would like to claim that when you say nanogenerator, you must think about it must be nanostructures or nano something, but it's actually in the very beginning, because Professor Wang is actually as an expert in the nanomaterials. So they are using some nano structures or nano materials to realize this kind of phenomenon. But when it comes to be more general, and also a lot of efforts have been done, so this kind of phenomenon has not limited to the nano scale. It can be observed and repeated in even the macro or even the macro scale. So, but because of he choose to make it specific, so the nano is still remain in the name. So that's actually the story of it. So when we talk about this phenomenon, there actually it's an electronic device for mechanical to electrical energy conversion, and including two main steps. The first step is the triboelectric effect. That means we have two devices or two materials that contact, and they can generate different charges, right? The positive and negative. And when we after that, we will have the like the periodical or some other like the mechanical stimuli to make them separate and contact, or even have different displacement. Then we're using the electrostatic induction to generate the output. So that's actually the basic ideas. So with this kind of sensors, what can we do? So that's actually my research and my work. My group is focused on. So first of all, let's think about if we. This is actually our my first job when I be independent researcher. So so Ramesh, can you think about this one? If as I mentioned that when we touch different materials, they generate different charges, right? If you think about that, if you wear cotton and wear the wool, which one will generate more charges? Right? So every time when I in love voice, okay, and because it's very north and very dry, so every time in winter you will wear a wool sweater, I'm afraid of open the door, right? But if you wear cotton, right, you're not. It's good. That's actually because the different the wool can generate charges. So that's actually Dr. Isara is investing why wool generate charges. But for me, I just observe this phenomenon. I utilize this to help our robot or to design such a sensor to distinguish what kind of material you are touching. So that's actually the very, very basic story. But to realize this one, we need a lot of very standard and very, very, for that one, it's only the observation and kind of ideas. But when you really, really integrate this kind of idea into a real working system, there's actually a lot of engineering and the scientific work to do. So this is actually our first idea. We are utilizing a fingertip tactile sensor. The first can not only detail the pressure or surface property like the texture and some other like mechanical structure, but also can be used for the materials or some object identification. So that's the actual idea. So we will briefly introduce how we do it. Well, so we designed this kind of very simple but powerful like sensors with a grading structure. If you're familiar with the flexible PCB or printed circuit board printing, it's quite cheap. And this kind of structure is flexible, can work as like the tactile sensor, but also can be used for the sensing. So we are optimizing different like the structure size, structure like the distance, and to find the best. If you are doing with the signal processing or some other things, the signal attitude is not the most important, but the SNR, the signal to noise ratio, sometimes actually we want to optimize. So we actually propose a kind of metric to determine which structure is the best based on the study. So we can find, so with this kind of square and equal like the width, well, we have the best SNR. So this is the first we are doing. And then to better standardize how the sensor can distinguish the different material. We have made some like the standard testing samples and also some like the mechanical texture samples. So we are actually we have implemented some kind of linear motor-based like testing platform, and we can see that the results is good. And with this kind of platform, and we can see that for different like materials type, with the same pressure and with the same like the mechanical stimuli, the output can be distinguished, right? For example, but here we see that cotton will have the better performance with our sensor, because our sensor has choosing a different it's different. And also when we see that with a different texture, for example, if we are passing through a smooth surface or passing through a different texture surfaces, the signal will reflect different frequencies and different waveforms. So that's actually the basic idea. But the problem comes to us. The sensor has only one-dimensional output. We actually want it to distinguish not only the texture but also the material. So what we actually doing is propose the signal decoupling method. So with one-dimensional signal to distinguish or recognize two different features. So how we do that is actually we are using some like a signal decomposition method. So here we are using a very mature method in the signal processing called wavelet decomposition. But also you can use some like Fourier transform or some other thing. But for our structure and our sensor, the wavelet works very well. And I will not go into very detail in this method, but we can see that with this kind of signal decomposition, we can, this is original signal, and we can definitely decompose the original signal into a macro. This is macro feature, and this is a micro feature, and in reflecting the frequency, reflecting the like the textures. So in this way, we can definitely using one-dimensional signal to detect two different or more features. And in that way, we are throwing the results into kind of very fancy neural networks to do. But why we didn't? Using we also can do that. We are throwing this kind of signals to one like neural network. They can also be distinguished. But why we want to do this? We want to be the result to be more explainable. So come here. So if we are, we actually have four different like the types. This is all for the materials. This is for different types for the textures. If we are using one like the neural networks, we can definitely distinguish 4 times 4 is 16 types. It's okay. It's very accurate. But well, this kind of model cannot be extended because we want the model to be like explainable. We didn't want the combinational results. We want the single, whether the figure is. and where the texture is. So that's actually the motivation and the why you choosing decoupled signal and also doing the combinational recognition. So this is some results I want to show you. We can do the real time like the texture and material recognition. And the recognition is really fast, within about 5 milliseconds. Because we're using very, very low weight neural networks. Okay, and the second one is actually we're doing some like the Braille recognition for the blind people or disabled people. So it's actually for the if you are having an accident and got temporary blind, and you still want to recognize some like the Braille. So this sensor can be used for this kind of people. So for this kind of sensor, there's no learning rate. You just wear on this kind of sensor and you can read everything. Yeah. And the third one, I think, will be the most interesting because this comes from, but I still have some argument with my wife because this is actually why I want to do this kind of tactile sensor and materials sense. It's come from a very, very embarrassing memory when I was an undergraduate student. There is a very good buffet near my university, and I go with my roommates to go to the buffet and want to find very good fruits. But when I see the apple, I just grab it. It's fake. Oh, it's just made of sponge, right? But only when I touch it, I know it's fake because all the colors and the shapes are all the same, and even better than the real one. You know, the real apple sometimes looks ugly, the delicious one. But that's actually a story, right? So and the same thing, but this is actually why the tactile sensor is very important. Even though may some of you are doing the computer vision or the video-based recognition, image processing, it's really powerful. It can solve a lot of by 99% of our current application. But why people still need tactile? Because in some extreme cases or make more natural human machine interactions, tactile is very essential. Even though vision can make 90% tough. So that's actually the motivation. We actually, with this kind of sensor, we can distinguish whether this is fake apple, this is real apple. This is a fake act, this is a real act. And also that's actually the motivation of my work. So, but my wife still thinks it's useless. But I try to argue with her, right? Because she's a really, really practical lady, right? He thinks it's useless, but we still want to argue and persuade her to appreciate this kind of work. Okay, well, to make this is actually a first idea, but as I mentioned that in the previous work, the system is still not perfect because we have to keep the pressure every time consistent to better distinguish the materials and the textures. So, but that cannot be solved without only single structure. So what we are continue to doing is actually to better, or actually what we can do is just include more data, the pressure data. So here we are actually including another thin film. It's a photoresistive film, and Isara is very familiar with that. We actually want to increase, or actually increase more dimension of data. But what we want to do, we want to solve, when we increase the one dimension of data, we don't want to keep it consistent because, you know, keep the pressure consistent will be another issue. you have to very precise robot control. But actually, when human doing the tactile sensor, it doesn't matter, right? Your hard handshake and soft handshake still give you some information, right? So that's actually what we are thinking about. And also think about how you touch with the glass, right? You will touch. Sometimes you will touch from the bottom, like the top. Sometimes you will touch the bottom. So, but robot, you can only touch with our like the specified road. So that's actually we're going to solve is the way how the robot interact with the object. So we are increasing this kind of route, and to make sure every direction is included. So with this kind of time series signals, we will have more robust recognition. Once you write, this is kind of vertical, this is horizontal, and some other trace. So this is actually what we are going to do. With this kind of more dimensional data and more like the flexible traces, actually we are increasing the recognition and increasing the flexibility. So here is some results. You can see that the red one is actually the pressure. So in this one, we don't have to keep the pressure very consistent. It can be arbitrary. It can be very flexible. And even with this kind of pressure, we can recognize it very well. So that's actually the revised and improved version of our previous sensor. I try to be quick. Okay, and with this kind of sensor, and what we are going to do is actually solve another challenge in the software robotics, which is actually really hot topic in the robotics field. It's actually we want to the one thing is for the robot sensor, there are actually two main tasks for the software robot. Actually, the first one is the environmental sensing. You have to sensing the external environment, external object, but also you must be very aware of your self-state sensing, right? Your self-state. How even though you didn't grab something, you must know how your state is. So actually, this is a two very important things. So actually, we are doing this kind of new electronic skin method with the liquid metal and with a lot of material. That's actually why our group is interdisciplinary. So we are actually we can design something from the materials, from the fabrication process until to the whole system. So actually we're fabricating this kind of electronic skin, and which can working with two modes. One mode is when we put it in the Triboelectric mode, it can be a sensor, can be a kind of touchless sensor from other sensor. And we can also change it to a piezo-resistive sensor. So this is the two modes, but with the same materials. And we are actually using this kind of software robots and sensors.
The soft robotic hand, equipped with a skin, can distinguish the grease category by analyzing the frequency response from shaking.
Touchless sensor. We can touch some box and inside components. Very accurate. Just based on the robot itself sensor data. And now we're working on it cannot only recognize what the object
The logistics industry can also use the self-vibration states to inspect packaging quality.
Or the weight and some other more information of the object. Okay, so this is the first part. We are actually aiming at to design better sensor, good sensor, and the low-cost sensor. But with this kind of sensor, and can we improve the robotics grasping and recognition? So this is the second part. And so with this kind of sensor and with this kind of techniques and the preparation, we are actually first to solve the most challenging part in the robot grasping. As we all know that computer vision has boosted the robot sensing in many ways, but there is still several open problems. The first problem is to deal with the transparent objects. So only with the transparent object, we need a textile, right? Because the transparent object usually has less or no textures. And sometimes the surface, like light, will change it with the environment, right? You cannot tell whether it is real like this one. When the robot see the transparent object, sometimes will be horrible. And even the human, right? I have a corgi dog, and me, we have very clean and white glass in my apartment. So sometimes if we didn't take care, we just kick the glass. So that's actually why we need some tactile to do so. And also for the smooth surface, sometimes hard to hold and easy to scratch. So that's why we want to solve this one. So let's look at this one. Most of the existing work deal with the transparent objects can only assume that the object is placed on some flat surfaces, and also they are not stacked to each other. But how to deal with the overlapping stacking or like in many the highly dynamic scenarios is really hard. So actually here we propose with the electronic skin and also some visual-tactile sensor, we can doing this kind of recognition and grasping. So this is quite simple. So this is a camera-based, similar to the gel side, but with this kind of software narrowing, we are having the TNG and some other like the electronics thing to make whether it's touched or not. And also with the camera and some other materials particles, it can be very consistent when there is a different light and can do the reconstruction. So this is a very simple but good ideas, and we solved this kind of touching and for transparent object graphing. But we actually propose 3 different ideas. If you can see something, just graph, right? If you cannot see it, or you cannot see it clearly, you just see and touch and adjust your graphing. But if you are blind or if your vision is interrupted, you can also still to explore the world with the tactile. So this is actually our solution, very similar to the human interaction in the real world. So let's see some results. And also this kind of breaker not only can sensor, but also can grasp with negative pressure. Since we're actually not the expert in the control field, so we use a very naive and intuitive control strategy, but still the sensing property, sensing capability and grasping is good with this kind of strategy. And this is the second one. Previous one, because we are solving the flat and very simple background, and here we can deal with very complex background, different heights and different textures and different time. Yeah. And once the graph, it can recognize which kind of object it is, and then realize the grasping. Okay, and here is actually the most challenging part, and also the reviewer when they see this kind of things, they're really excited about that. This is because in a highly dynamic field environment, especially in a moving water, and you see the camera-based, the computer vision-based graphing and the sensing will totally in vain. And with our touching stuff and tactile stuff, we can do really good sensing and grasping. It seems like you grab the fish, right, in on water. Yeah. I would like to say the searching strategy is also very naive. We are not utilizing the complex one. we're using the brute force surgeon, but in third try, and then we can see we grasping something, we are touching something. And we are just adjust our grasping position to sense and then grasp. Okay, successful. So that I would like to say that before our work, there is no efficient and effective way to do this kind of underwater searching and exploration. And okay, so with this kind of thing, actually we are also doing some other very interesting applications. This is actually come from the the COVID, and so in China, a lot of like the swab sample almost every day in Shenzhen. Maybe some from China you know that. So actually, this caused a lot of waste of labor and also the anxious of the because my mom actually she's a doctor and she has to go every day in the front line to do the swabbing sampling. So me and my student actually proposed a kind of software robot based swab sampling. And but when you are using robot to sample and with using humans to sample, most of the difficulty is to make it like comfortable. And if you're a robot, you are always afraid of that robot can hurt you and damage your throat, something like that. So actually, we are using this kind of visual-tactile sensor and also with the software robot to solve this kind of problem, and also without any sacrifice on the efficient, because sometimes it's soft, it must be soft or must be comfortable, but if the efficient can be lower than the human or some other thing that cannot be used, that's actually our motivation. So we propose also the similar structure with this kind of jamming gripper and with this kind of very chip. And we also propose some kind of framework. It's very complicated, but I will show you the applications. And sorry, okay, how it really can be realized to do the swab sampling. You can see that even very small force can make the sensor to be sensor and sensitive, and also it's all water resistance and it can be cleaned in a very simple way. And we're also doing some human tests, and for me, I think the comfortable is okay. Yeah, better than my mom. Because she usually touched very hard to get the sample, right? This is my student, yeah. Yeah, the force is really small, but the efficient is really good. And also with this kind of structure and the software robot, we can also do some other like that. The first one is doing a very precise like the grading tool for the for surgery or for some other things. And also we can do some like the fitting tool for the Parkinson and outcome seniors and care assistant. It is really stable and robust. Okay, and following this kind of route, and we also propose another interesting idea is because how we can give more like the information or more control capability to our previous sensor. So actually, what we are going to do is actually adding TNG or adding like the remote control layer into our camera-based sensor. It's actually very simple, but the idea is very simple, but the results and effect they're really good. We actually after we realize this one, we going to see is there any like inspiration from nature. We are lucky to find the Playtus, which is a really cute animal in Australia, and actually this Playtus is almost blind because his eyes cannot work well, but he can do really good hunting for underwater fish and with his beak, with his nose. And the nose has two different functions. One is electricity sensing using some other like the receptors. And the other thing is actually the tactile sensor to do some like exploration. So actually there realize two different like functions. One is the touchless control, touchless sensor, and also one is the tactile sensor. So we actually propose this kind of structure to realize or similar to the Playtus. And well, I would love to talk to Marsh on the technical details. I would say with the TNG and the optic tactile, we can realize the two kind of sensor very well. And it can also do some other similar, right? If you see aware of my research, you can see a lot of similar things. We always want to do some material recognition and pressure recognition and something like that. And but this one is actually the first like the robot in the world, or first sensor in the world that can not only do in the tactile sensor, but also can do the touchless control with this kind of things. I will show you some results. Let's see. The left up is actually where we can use the kind of sensor to sense whether the object is the distance of it with the different like amplitude of the output of the triboelectric layer. So this is touchless sensing, and also we can do very good like the pressure control and the texture reconstruction with the camera, the optical based tactile. And this is and you can do twist, and you definitely know what actually your touching is. And this is the second one. And the third video, let me show you it. Similar to our first like the tactile sensor for material identification, but the good thing is with this kind of camera-based like the sensor, we can extract the pressure in a more effective way and do the texture reconstruction. And we can do very good recognition. And the fourth demo is we can do some like wireless control and with different hand gestures. And because our triboelectric layer, they can sense wireless, sense the control command in a wireless manner. All this has been done with the tactile, with the sensor, without any vision. I think that's second part. And well, here is some like integration system. We are actually integrate all these things together in the air, and with the wireless control and the finger can do the sensing and the moving in a totally touchless way. And either with transparent or non-transparent, they can all work. And can also do some manipulation thing. Okay, and then will be the final movie, and you will be more aware of it. And with this kind of things, we can also do the wireless control in underwater, because of the similar to the Playtus, because our sensors, our cameras, they all can send signals even in underwater. Do you know for TNG, the underwater sensing is another problem, but here we actually using another good issue because TNG can work together with water as the big capacitor, and you can definitely do some like the receiver and wireless monitor like receptor. So we actually utilize this kind of good things, and we can do the underwater grasping and the reconstruction. We can see what we are graph. Yeah, we can see the textures. Okay, I think that's most of the part of our today's talk. I would like to say actually my group is actually focused on the flexible sensor, but we actually have broad interest in not only the IoT but also the human machine interface. Actually, I would actually it's a really interdisciplinary areas. We can do a lot of the device and also previously a communication guy, so we know how to optimize all these communication and control strategies. But also what we are really care about is how to solve the real open problems with general method, not limited to some specific sensors. So and I would also like to thank to all my students. Actually, I now have 10 PhD students and almost 20 master students. It's a really big group, even bigger than my postdoc supervisor when he was in the United States. And without them, I cannot do this kind of really interesting project in the past 3.5 years. And finally, I would like to thank you all for the listening. And this is my group's QR code, and you can scan it and to directly direct you to my webpage. And thank you very much.